what are the internal factors for which will affect the time to ignition? Thermophysical properties, rho, C, K, etc. Thermochemical properties, what is the calorific value? Then see, the pyrolysis temperature, heat of pyrolysis, one more characteristic which will come into play. So these can be this. Then moisture content, if the moisture content is higher, we need to supply the latent heat or temperature has to be increased to 100 degrees centigrade to remove the moisture. So this is another issue. Moisture content is higher, then time to ignition will increase. Then radiation properties, as we have already seen, structural absorptivity, transmittivity, etc. of the solid surface. Because if from the surface to the ambient, if there is a radiation loss, then that will increase the time to ignition. When there is a heat loss from the surface to the ambient, then the time to ignition will increase. Then there is a solid surface and gases are there above this, pyrolysis gases or volatile gases. What the spectral transmittance of these gases will also affect the heating. Okay, that is another thing. Then kinetics of the thermal solid phase decomposition and composition of the decomposition process. This is very important. Okay, so let us see this solid surface which is heated, Q dot G2I, and there is a heat loss, say QL, and there is heat conduction, QC. So now there is a growth of temperature here. So T initial temperature to T pyrolysis temperature. Okay, now to get this we need only some heat balance. But what is the mass flux of the vapor coming out or gases? Not the vapor, gases. What are the mass flux rate of the gases coming out will be equal to A times exponent of minus EA by RUT, and so you can say oxygen concentration, something like that, 2 power n. So now if you say this is the mass flux which is coming out of the volatile gases. So unlike evaporation of a liquid fuel, the thermal decomposition of the solid phase is modeled using a kinetic expression like this. Modeled using a kinetic expression. Okay. So in the case of liquid fuel, we just use Fick's law, correct? So we said that mass flux will be equal to rho A VA or rho F, we will say rho F VF, mass of F will be equal to, which will be equal to rho F VF YF minus rho DFB DYF by dx, something like that we wrote. So that is Fick's law. Mass transfer, very simple mass transfer thing. But here you can see that here we have to substitute surface temperature. If this mass of the fuel at the surface, so surface temperature I will substitute here. So here it is kinetic expression which we use basically. That is one of the difference. Okay, now second is the composition of the decomposition. What are decomposition products? These are volatiles basically. So what is the composition of that? We don't know. So volatile composition can be a mixture of CH4, C2H2, C2H4, CO, CO2, H2, N2, O2, etc. Several unsaturated and saturated hydrocarbon, CO, O2, N2, everything will be there in this volatiles. Now, the composition of this, that is, what are the volumetric percentage of each component in the volatile, that is not constant. When a liquid fuel evaporates, see for example, I have a liquid fuel which is say N-heptane liquid. So in the vapor phase, I will have N-heptane vapor. That's it. So, the composition is very much clear in the case of liquid fuel. But in the case of solid, when volatile gases come out, volatile gases can be composed of several gases like this, and the percentage, volumetric percentage or mass percentage of these cannot be easily analyzed, because it will vary. The rate at which we can say that the solid has to be heated till a temperature of Tp, from initial temperature of Ti, in order to get the volatile gases released from the solid surface. But the composition can depend upon the rate of heating of the solid. That is, how fast Ti is increased to Tp, the composition also can vary. Further, the Tp, after reaching Tp, the temperature of the surface need not be at Tp, it can further increase due to the incoming heat flux, or the flame which is formed over the surface can give heat feedback to the surface, and the temperature can increase beyond Tp also, beyond Tp. So, now what happens when the temperature increases beyond Tp, this mixture will change its composition. So, unlike the N-heptane vapor formed from at the surface of N-heptane liquid, we can say this is okay. Based upon the surface temperature Ts, the mass fraction of this vapor at the surface can be determined, and it can be lower or higher. For example, if surface temperature is very near to the boiling point, then YFS will approach 1 value of unity, or else it may be very low, say 0.6, 0.7, something like that. So, the composition is still definite, there is no problem. Okay, let us take an example where I have a binary fuel, liquid fuel, N-heptane mixed with say N-hexane. In that case also, in the vapor phase, I will have N-heptane and N-hexane vapors, but different compositions. But based upon the temperature Ts or pressure at the ambient P infinity, we can exactly say what will be the composition of the vapor phase. See, in the liquid phase, N-heptane can be 60%, N-hexane can be 40%, but in the vapor phase, they cannot be at the same, because of the differences in the boiling points of these two liquids, latent vaporization, etc. It may be, instead of 60 to 40, it may be 55 to 45. That can be there, but the composition can be determined easily. But on the other hand, if you go to the volatiles, the composition volatiles are very tough to fix, because based upon the heating rate, based upon the surface temperature which can increase beyond Tp, we will see the volatile composition can change. This is very, very important point to note. Now, the sixth point is, so okay, before going to sixth point, one point I have to, you can classify the solid as charring solid or a non-charring solid. Charring solid is one which will leave carbonaceous material like fixed carbon and ash. When the volatiles are released, there will be fixed carbon and ash, which together are called char. On the other hand, if you take non-charring material, solid material like say a plastic, polyethylene or PMMA, etc., we will not have the char formation. Some impurities may be there. So, the char formation will also affect the decomposition of the solid or the volatile release. Okay. So, for example, I will come to that little bit later, because of the fact that when char is formed, the char can be heated to higher temperatures. Again, the volatile which is coming through that char layer can be heated up and the composition can change. Okay. So, then next point is the chemical kinetics of the gas phase combustion. So, this will be actually very fast, but this chemical kinetics depends upon, see, for example, in the liquid phase, you know, liquid fuel case, you know the different amount of vapor will be there, and we are talking about the reaction between a particular vapor, say N-heptane vapor or a mixture of N-heptane and N-hexane vapor with air. So, it is easy to calculate the kinetic parts there, but in the case of the gaseous combustion over a solid fuel, where the volatile itself will have different composition, how will you determine the kinetic rate? Because there are several fuel components in this, CH4, C2H2, C2H4, CO. So, CO and this C2H2, C2H4 will be reactive, much reactive than CH4. Hydrogen will be very reactive and so on. And obviously, you have a oxygen content also which is coming out. So, you will see that the chemical kinetics, determining the rate at which the chemical kinetics can happen in the gas phase due to the burning of the volatiles is not very easy or straightforward. So, that has to be clearly understood. Now, when you take plastics like PMMA or polyethylene etc., the plastic can melt, or when the plastic is heated, locally some bubble formation can occur. The bubble can burst from the surface and so on. So, these are all the features which we cannot easily analyze. Melting, so that is the melting point for a solid. So, when the temperature reaches the melting point, it can do, but the bubble formation etc. can be due to impurities, can be due to some moisture which is there in the plastic itself, which can evaporate and form bubble, and the bubble can burst. So, that means that there will be a very complex phenomena for pyrolysis when this occurs. So, pyrolysis process itself, which is going to affect the ignition, has lot of complexities. So, based upon several factors, the pyrolysis has to be understood. Why kinetic is important? Because ignition is a premixed combustion, correct? So, kinetic is very important, but what is the premixed reactant what we have, that should be known to us in order to analyze that. So, these are the factors which affect the time to ignition. Now, further factors which are going to affect the time for ignition is the heat and mass transfer associated with external heating of the surface. That is very important. If you have a, as I told you, there is a solid surface, there is a heat which is coming in. This can be due to convection, radiation or conduction etc. And correspondingly, there is a net heat coming in. So, because of the heat loss and because of the conduction etc., there is a net heat which is coming in, and due to which some mass transfer occurs from the surface, mass flux into, say, it will have its own enthalpy. So, that will be the energy which is released out of the solid surface. So, now when you heat up this at a faster rate, for example, the net heat which will be, see this, if this is higher, then you can release the mass from the surface at a faster rate, and the surface temperature Ts can increase at a faster rate. As I told you, there is no, basically there is no constant temperature for the surface to attain. When you go to for say melting and evaporation of the molten solid, then that is a different case. But in general, what I am saying is this surface temperature need not go to an equilibrium value, okay, like what we saw in the liquid cases. So, the rate at which the surface is heated, that will determine the rate at which the mass is coming out, and this is dependent on the surface temperature. So, we need a kinetically controlled mass transfer rate, what we have seen earlier. So, basically what the ignition models will do is, they will do this thermal balance like this, simple thermal balance. So, now here I have to add basically minus m dot double dash into H delta H, correct, that is the thing which is coming out, okay. So, the how fast the solid is heated from its initial temperature Ti to the pyrolysis temperature, volatiles will be released and ignition can take place. So, the ignition models will focus more on the thermal based models. Okay. Now, why we do this? Why we are not taking into account of the gas phase reaction, etc.? Because even though we do not know exactly what is happening in the composition of the volatiles and how the gas phase reactions are to be controlled, we are sure that the gas phase reactions will be much faster, because you have lot of unsaturated hydrocarbons, hydrogen, CO, etc. in the volatiles. So, that means that the reaction rate will be really fast when compared to the solid heating time. Okay. Even if you have very high heat flux, etc., the time required to increase the solid temperature will be quite high. Time required will be quite high than the gas phase reaction. So, let us see some example from Quentry. The time, typical time which is used for a reaction to complete will be of order of 10 power minus 4 seconds. Now, where volatiles are coming from the surface of the solid, it goes to the gas phase, mixes with the air. So, this transport of this plus mixing will be of order of say seconds, some few seconds, order of say 1 second, I will say 4 seconds means order of 1. But the time for inert heating the solid to the, so that is T pyrolysis. Pyrolysis time will be 120 seconds, order of 100 seconds. Okay. So, order of 10 power minus 4 seconds is the gas reaction, which is very small. Then the mixing time is order of 1 second, pyrolysis time is order of 100 seconds. So, that means that pyrolysis time will be the rate controlling. That is, the heating of the solid is the main thing here. So, time to ignition is basically controlled by the pyrolysis time. So, for pyrolysis time we have to do several tests exposing the solid to different heat fluxes or heating rates and see how fast dt by d time occurs. That is very important for us. So, this will determine the time for ignition. Okay. So, even though we have seen in the liquid burning that the liquid evaporation is the time limiting factor or the rate controlling factor for evaporation as well as the combustion. In this case, it is the time for inert heating of the solid, that will be the important, that is the pyrolysis time basically. So, now we will talk some few points about types of ignition. Now, for this we need to consider a charring fuel or a non-charring fuel. Charring fuel which leaves a carbonaceous residue, wood is an example for charring fuel. So, wood leaves a fixed carbon and ash together, which is called char, and polyethylene is an example for the non-charring, it is a plastic or we can say polymer. Okay. Now, this polymer is made up of monomers, generally liquid. This polymer is a solid which is made up of monomer which is liquid. Several monomers, so subject to some temperature and pressure etc. will cause polymerization. Now, let us first talk about charring, taking the example of wood which is used in several applications. Okay. So, wood is a heterogeneous means, homogeneous means that is only one phase, either liquid phase or solid phase or gas phase, but heterogeneous means there are several phases. Trapped moisture is there, the liquid water, then volatiles, gaseous, trapped gases, then solid, fixed carbon, and again solid which is mineral ash, inert material. There are 4 components which are actually got from proximate analysis. We have seen this already, proximate analysis. So, the percentage of moisture, percentage of volatile, percentage of solid carbon and percentage of ash mass basis can be determined from the proximate analysis. So, now, since it has say liquid water, volatiles, this carbon and ash, so solid, liquid and gas everything is there. So, wood is a heterogeneous and it is called solid because it is in a solid form basically. So, what happens when you heat this due to any external heating? When the temperature of the wood reaches about 100 degrees, the volatile, see the moisture, when the temperature is increased to 100 degrees, say from 30 degrees to 100 degrees, then the moisture will come out, vaporization come out, water vapor will go out. Then if it is heated in the range of 350 degrees centigrade to 400 degrees, then the volatiles are released. So, typically the pyrolysis temperature is around 350 degrees centigrade to 400 degrees centigrade, we can say. Then only they see like flash point, the minimum temperature where enough vapors come out of the liquid surface to cause a premix combustion. We can say that when the solid is heated to say 350 degrees, some vapors will, gases will come out, some gases which are called volatiles will come out and a premix thing can be formed, and when the ignition source is there, then instantaneous flame will be got. So, that is the range of temperature 300 to 400, even it can go to 450 degrees in some cases where volatiles are released. These volatiles which are released will mix with the ambient air, and based upon how much volatiles have come out, it may form a mixture, reactant mixture within the flammability limit. So, lower flammability limit to higher flammability limit. Basically, we are talking about the mixture reaching the lower flammability limit so that it can be ignited. But for ignition, you need a external ignition source, that is the pilated ignition. It may be spark, then I will say pilot flame, etc. Now, if the surface temperature of the solid Ts, okay, is more, say it is increasing, as I told you, the surface temperature need not be at the pyrolysis temperature for pyrolysis to be released. If continuously pyrolysis is occurring, surface temperature now reaches a value of say 800 degrees centigrade for example. Now, volatiles coming out of this will also be, volatiles will be at say 800 degrees centigrade, approximately that temperature. When the mixture forms, the mixture itself will go to this temperature because of the fact that volatiles are mixed with the ambient air. So, in this case what happens is the mixture is already at a temperature called auto ignition temperature. So, auto ignition occurs without requiring a pilated ignition source. Auto ignition occurs, there is no need for putting a spark or flame. In this situation, when the volatiles are coming out is at a higher temperature and a mixture which is formed which is more than the auto ignition temperature of the mixture which is more than the auto ignition temperature. So, this is important point we have to understand. So, pilated ignition or auto ignition also can possible. So, now fixed carbon. So, that is what I am saying, that when we take a solid wood, now heat comes in, then volatiles are released. So, moisture is first released, then volatiles are released. Then what happens is a surface or layer of char forms, char which is nothing but fixed carbon plus ash. So, that layer forms here. So, this layer can be heated up to 900 degrees centigrade. Okay. If the char layer is heated up to 900 degrees centigrade, oxygen from the ambient can come and surface reaction can take place. Correct. We already seen this also, glowing reaction, glowing ignition which we say, or smoldering. Okay, glowing ignition or smoldering will occur. once it is heated to 900 degrees. Now please see that due to the oxidation, temperature can still increase. This surface temperature can still increase to say 1000 degrees, etc. Now what happens is this will heat up the wood, raw wood, which is present below this char layer, and volatiles will be released. So these are volatiles which are released. These volatiles will be at higher temperature and a flame can be formed due to the release of the volatile because of the auto ignition now. Okay. So the burning of wood is very complex phenomena. Even the ignition of wood itself is a complex phenomena, taking into account that the volatiles start to release in a small range of temperature like 350 to 400 degrees, but the surface temperature can still be increasing and volatile release can subsequently simultaneously happen. Now volatiles which are released when the surface is heated to higher temperatures can reach a temperature of auto ignition temperature, so that the mixture which is formed can auto ignite. Now after the surface reaches the temperature of 900 degrees, all the volatiles are released, the char layer is formed. This char layer can attract oxygen from the ambient and surface reaction can take place. The surface reaction is an exothermic reaction between C plus O2 giving CO2. So this is CS solid. So this reaction can occur, which is a surface reaction with red hot color, red hot surface we can see, radiant red color, and this is called smoldering basically. So now oxygen can penetrate inside, volatiles can come outside, and since the temperature is high enough, we can have an auto ignition straight away. So when you take charring, the type of ignition possible in a charring type of material is pyrolytic ignition, when initially the char is not formed, but the volatiles are released because of the heating of the wood or any charring fuel to a temperature around 300 to 400 degrees centigrade, because the 400 degrees centigrade is not auto ignition temperature. 800 degrees centigrade, something like that, will be the typical auto ignition temperature for several fuels. So what we are observing here is, for the wood to be heated up to release volatile, the temperature range is quite below the auto ignition temperature. In that case, the volatiles which are coming out will not be at higher temperature, so we need pyrolytic ignition. But if the surface is heated up to auto ignition temperature or more than that, then the volatiles which are coming out can be at a temperature which is more than the auto ignition temperature, or it can ignite without the requirement of the pyrolytic ignition. Now let us come to the non-charring solids, where basically I told you plastics and polymers will be there. Now they will not produce any carbon residue upon devolatilization. Devolatilization is actually release of gas. Okay. So now when you do this heating of the non-charring fuel, there is a temperature called softening temperature. A rigid plastic can soften. It can melt when it reaches the melting temperature. Okay. Now please see that pyrolysis temperature is one in which the devolatilization takes place, where the gases are released. Now this gas release can be due to direct sublimation, solid to straightaway vapors, or it can be first melting, forming of the liquid surface or thin film of liquid, then that will vaporize. Okay. So now pyrolysis temperature can be close to boiling point when melt is formed, or pyrolysis temperature can be sublimation temperature when there is direct sublimation. Okay. So other than that, we have softening temperature, which is very low temperature at which the plastic can, rigid plastic can deform, or it can have some softening tendency. Then again it depends on the type of plastic what you use. So melting temperature, you know that where the melting can occur. So if you take PMMA type of thing, then or polyethylene, first melting will occur, then vapors form. And even in PMMA, we can say that there can be sublimation. Okay, so now the gas or vapors, okay, when melts and evaporates, vapors are formed, which leaves the solid, need not be pure monomer component always. Okay, but generally, as I told you, PMMA, let us say, goes to its monomer MMA, which is liquid. But in this case, it is correct, like to say that monomer can be formed, or predominantly in the gas phase, the monomer vapors are present, that is fine. But in always it is not so. It can be, the gases which are coming out can be multi-component in nature in some cases. So, that is what we have to understand. Now, the gas mixture leaving the solid must form a vapor air mixture or gas air mixture, which will be at least in the lower flammability limit. Then only a piloted ignition can be done. Now, if the mixture somehow reaches due to heat transfer a temperature of auto ignition temperature, then auto ignition can occur. So, in this case also both can occur, but predominantly you will see that the temperatures at which the pyrolysis occurs will be much lower than the auto ignition temperatures. Since the temperature of the non-charring solids cannot reach a higher value, because if it melts, for example, if it melts, then it will reach the boiling point, or it may sublimate at a constant temperature. These phase changes which will occur at a given temperature based upon the pressure. So, these temperatures cannot be normally as high as the auto ignition temperature. So, auto ignition need not occur. Okay, so I will stop here. I will continue in the next class.